in this question, we are tasked with finding two different things. One is the various positions or locations in space at 3 different times, and whether or not this object ever changes direction, and if so, at what point in time does that occur. So because it's part B, the question B is so straightforward and simple, we're going to answer that one first. And that's going to be basically just look straight off of your graph. And in our graph, we can see that the velocity, because this is a velocity time graph, and that the velocity is positive until 3 seconds. Now remember that the sign of velocity is equal to the direction, so that it's moving, currently moving. So whenever the velocity is 0, you have a turning point, and that occurs right here at 3 seconds. So this object, if we were to be looking at what was happening in a straight line, it would have been moving in this direction very quickly, slowing down, stopped, and then start moving back in the other direction. So for question B, we would say yes, and that would be at 3 seconds. Okay, now question A is a little bit trickier. Okay, if you recall, the area under the curve of a velocity time graph is equal to the displacement. The problem is we want to know what the position is, for which I've got a typo here. This should be position. Okay, well, position and displacement are not the same thing, but they are related, because displacement is equal to the change in position, which is x final minus x initial. So we're going to be using this equation primarily to determine what's going on. All we have to do is figure out what the area is underneath each curve during that particular time interval. So for the first question, we want to know what is the position at 2 seconds. So we want to know what is x2. And so what we're looking at is the area from 0 to 2 seconds, and so this is how it's bounded. All right, that's the area we're looking for. Now, this is not a triangle or a rectangle, so it's not quite so straightforward. It's a trapezoid, and so we'll just use the trapezoid equation to determine the area under that curve. So the area of a trapezoid is equal to 1/2 times base 1 plus base 2 times the height. So base 1 is going to be right here, it's going to be 4, because this is where base 1 is at. Base 2, we could say, is 12. So this is going to be 1/2 times 4 plus 12. And then the height is going to be 2 seconds. Okay, so what we have here is this 2 cancels out with that 1/2. And we have 4 plus 12 is 16 meters. Now remember, that's the displacement. Okay, so there's a relationship. We're going to use this relationship, and we get the final position is equal to the displacement plus the initial position, or 16 plus 10, which is 26 meters. So that's our answer for time t equals 2. Now at time t equals 3, we're just looking at a triangle, and so the area is equal to 1/2 the base times the height, which is 1/2 times 3 times 12. And so this gives us a displacement of 6 times 3 is 18 meters. And now we know that x final is equal to d plus x initial, which is 18 plus 10, or 28 meters. Finally, we get to the position at t equals 4 seconds. Now, before we do this, let's just kind of conceptualize what's going on here a little bit. What we have at 3 seconds is a change in direction. So what we're saying is from here to here, this time interval, delta t, was 3 seconds, and the displacement from one side to the other was equal to the displacement was equal to 18 meters. Now this is x equals 10, and this is x equals 28. Now we have a change in direction at 3 seconds, which means the car is now moving back towards the left. So we expect a position which is going to be less than 28 meters. Now there's a couple of ways of calculating the total area. Keep in mind that the area under the left side is positive, and it's positive because it's above the x-axis, and the area here is going to be negative. Okay, so this is going to be, the area from 3 to 4 seconds will be subtracted from the area of 1 to 3 seconds. Okay, so the displacement then is going to be equal to the area of the large triangle minus the area of the small triangle. Now the large triangle, we already know that that's going to be equal to 18 meters. Now the small triangle has a time interval of 1 second, and it has a height of minus 4 meters per second. Okay, so we could say area large plus area small, where it becomes 18 meters plus a negative 1/2 times 1 times 4 is going to be equal to minus 2. That's a minus 4. So we get a minus 2 meters for that last 1 second time interval. So our total displacement now is 16 meters, and x final is going to be equal to 16 plus 10, which is 26 meters. And that's exactly what we expected based on our conceptual understanding of the situation. So right here is x4, which is equal to 26 meters.